Alright guys, welcome back to C++ for Java programmers. This is going to be the 6th lecture in the course. I am still a little bit behind, and with some luck, this is the week we'll be getting caught up. So I know I thank you guys for being so patient with me as I've been going through my recovery. I really appreciate that, and I really appreciate all the messages. It's meant a great deal to me. Alright, so as we get started today, a couple of reminders. I haven't done it yet. I'm going to build this template as I go through and record the lecture, but there will be a template available that you can download and follow along with today's work. There's also going to be a PowerPoint for the slides. I've got a couple of slides. Most of what I'm going to do with the slides is actually develop them as I go through and type on them and modify them. So the slides aren't going to look exactly like what's going on during the lecture because I'm actually going to be using them as a live material. All right. Homework 3 will be coming soon. I'll just send an email when it's ready. And if you have any problems, go ahead and please continue to send me screenshots of weird error messages. Feel free to ask any question you guys have about the format of the homework, things that are going on with class. If you get something that you tried out and experiment on your own and you don't understand, just go ahead and put that on Piazza or send me an email. I'm happy to answer those. Alright guys, this is Mike after recording the entire lecture. Coming back, just so that you guys are aware, the video is 80 minutes long. It's about 30 minutes longer than a regular class. I could not find a good reading assignment to go along with some of the pieces of this, so I just sort of kept talking. Don't think of this as an 80-minute lecture. Break it up, watch it in some smaller pieces, and then think about that extra content as replacing the reading that you would do to go along with the class. Also, as you go through, there's a template. Now that I've finished, I can tell you there really is a template where I'd encourage you guys to pause the video and type the code yourself. That way, there's no way you'll get it right every single time. At least if you type like I do, you'll get some error messages that you'll likely learn from. So I'd encourage you guys to not just go stare at the final version or even just like watch the video passively, but actually sit down and go through this and try and type the code and do your own experiments. See, does this work? Or wow, if that failed. When you get weird error messages, go ahead, screenshot them, put them up on Piazza, and we'll talk about them together as a group. All right, have a great day. All right, as we get started today, the plan. We're going to talk a little bit about the C++ memory model. So what's going on inside of memory. And I'm really hoping this will help you guys understand pointers better. Pointers is probably one of the more difficult topics that, at least when I first learned it, I had to read that stuff a couple times before I understood. A quick review of references, because references are extremely useful for passing things to functions. And yeah, they're very similar to pointers, and people often confuse them. So I just want to make sure the distinction is clear. They're like easy pointers. All right, and then we'll talk about arrays in the context of the memory model and the pointer array connection. I've done pretty much what I want to do there, but I'm going to review with the diagrams. I do need to say a little bit about character strings or arrays of characters because they're terminated by a null character that's sort of hidden from the user. We'll finish up with multidimensional arrays and how to pass all of this stuff to functions. All right, so we're going to get started with a look under the hood and compile the code. First up on the left here, I've got some sample code. This is just coming out of sum.cpp. It's got declaring and defining a variable A, B, adding it together, whatever. It doesn't matter. This is just my fake arbitrary code that I wanted to have some code here to talk about. All right, when we push compile, the compiler is going to go through a number of stages. The first one is the preprocessor. That's going to go ahead and take all of your includes and just copy and paste everything from those files in that spot. It's going to take all of your comments and remove them. Then the next phase is going to go through and turn all of the code into assembly code as sort of an intermediate step. From there, that assembly code gets translated into machine code. So here I've got an example of some assembly code. We'll be moving one of the variables into a register, move another variable into a register, add them together. So this kind of matches what we might have going on over here. But check it out. We're no longer using the A and the B, coming up with C, which will end up right here in the same register. We're not doing any of that. The machine on the inside is only going to be looking at memory addresses. I just want to point out too that inside the compiler, it does need to know which variable matches with which memory address. So it's going to maintain this symbol table. And as we go through and talk about pointers and arrays, some of those things are locations in memory, where like a pointer is a location in memory, where I'm storing the address of something else. And I can change that to a different address and have it point to like a different array if I need to. And some of the things are just constant arrays. Like if I declare an array with the square brackets, that's going to be a constant array. I can't redefine that point. Technically it's a pointer, but I can't redefine that pointer to point somewhere else. And so the symbol table is going to treat this differently. It's not going to be, an array is a pointer to a memory address. It's just going to point to the very first address. So they're treated a little differently on the inside. And as I've gone through, I did a bunch of research and looked at what a lot of people put out there for memory models. And some people do list the array as a specific pointer that points to a memory address. You can actually print out the memory address of a pointer, and you can print out the memory address of the first element of an array. They're going to be the same for almost everything. I've never seen the compiler do anything other than that. So just a heads up that there are some pictures out there that show things differently, so there may be more than one option that compilers choose. All right, and then after the compiler is done turning all of the assembly code into machine code, it's just going to be ones and zeros that correspond to things like memory addresses and codes for these different commands. All right, when we start looking at the memory, so every process that we run, every program that we write has basically access to an entire virtual memory space equal to the size of the, on a 64-bit computer, 2 to the 64th memory addresses. Now, you might not have that much physical memory. Your computer is sharing the memory with lots of other programs. So there's a translation unit that actually maps this entire memory space, all the addresses that this program is using, to some physical memory. And that's all behind the scenes. We don't need to worry about that. Take operating systems. But as we go through and we look at their code, the very first memory address 0, is reserved. We're not allowed to write to that, which means that if we have a pointer and we declare it to be a null pointer, we just assign it memory address 0. And if we do try to write to it, it's going to cause an error. So the very first 0 memory address is reserved. Then all of the code is placed in the next block of memory. So this is address 0. As we move down, we're going to see increasing memory addresses. So the code here is just the compiled code, that machine code that I had on the previous slide, all the ones and zeros that describe the commands and the addresses of pointers and things like that, where it needs to go to look up data. All right, the next section is the data section. These are going to be reserved for global variables and static local variables, which I probably won't talk too much about. They're just things that are going to be resident permanently in the code and available from anywhere. Following that, we've got the main memory used by the code for variables and data. I'm going to start with the stack here. So the stack are just going to be the normal variables that we define in the process of running our programs. Like if I say int a or int b, it's going to reserve some space on the stack. And as I continue to use more and more variables, it's going to grow from high memory addresses to lower memory addresses. So we'll be filling in the bottom ones first and then working our way up. As we call functions, those functions will have local variables. Those are going to go on the stack as well. So we'll just have, some local variables for main. Then there'll be some local variables for the first function. If that function calls something, there'll be some local variables for that function. When the function ends, we delete all those. Technically, it doesn't do anything. It just moves a pointer indicating where the top of the stack is down to the previous function. And those local variables are no longer available to us. All right. If we need to reserve some memory and we don't know how much size we need, the dynamically allocated memory is all stored in a section of the memory called the heap. That's going to immediately follow the data. As we reserve more and more of that, it's going to grow toward the stack. So it's growing toward higher numbers. And these are things that we reserved with malloc or a new, or we create one of the dynamic built-in container types like a vector or a set or a map. Those are all going to be stored in a memory location called the heap. If we do use the new operator, it's our job to remember to delete this. If we use malloc, it's our job to remember to free the memory. Otherwise, we have a memory leak. And if your code runs long enough, eventually you will run out of memory. All right, let me pull up some actual code. We'll do a quick review of pointers, and we'll talk about how this fits in over here on the stack and heap. All right, so I put together some code to just go over a quick review of pointers and show the connection to that memory model I just introduced. So first up, all this code does so far is just declare some primitives. I've got integers x and y. Then I'm going to declare a pointer right here in line 15, and I'm going to give it the address of x. So this much right here, int star, says I'm declaring a pointer. And again, remember, I can put the star next to the int if that helps me remember that this is a pointer. Or I can put it next to the p if I've got more than one variable. I'll do that if I have a comma-separated list, and some of them are pointers and some of them aren't. I like the star next to my pointer, so I remind myself that this is a pointer and these are integers. All right, then I'm just going to print out a bunch of stuff, and I think it's pretty clear. Printing out the value of x, the address of x, right there with that command. And again, when I declare a pointer, I need to give it the address of a variable so that it knows what to point to. I'm printing out y, although I haven't done anything with y yet. In a moment I will. And then I'm printing out a whole bunch of information about the pointer. So p itself, this is the value of the pointer, and I've just given it the address of x. I'm printing out the dereferenced version. So if I want to use a pointer, remember I need to use the star to say, go get the information that the pointer points to. So we're just printing it out just like that. And then I'm printing out the address of the pointer as well, so that I know where to draw it in my memory model when I flip back to the slides in a second. Okay, let me go ahead and run this. I just compiled, tested it, made sure it was working. So here's what we're looking at. This is my declaring variables section. I've got x is 3, exactly like we would expect. The address of x, all right, it's going to be this long hexadecimal number. I'm going to ignore the first digits that are all the same. And this is stored at basically address 08. This might change every time I run the program, so on my memory model slide on the next page, I'm going to just change these numbers myself and make this whole thing a whole lot simpler. So forgive me, it's not going to exactly match the demonstration. All right, I've got y. Check this out. Integers are exactly 4 bytes. So this is beginning on address 08, blah, 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 08. 4 addresses later will be 9 A, B, C. So 4 bytes later will be OC. The pointer is going to be located, so this is the value it points to. Sorry, the value that it points to, this is the data actually stored in the pointer is 08. So it's storing the address of x right there. The dereferenced version of the pointer is the value. So trace the arrow back and get the value of x. And the address that the pointer is stored at is, let's see, AF10. That's going to be the four addresses after this one. So they're just stored in order, 08, OC, and 10. So let me go ahead and put those in my memory model on the diagram. One sec while I add those. All right, I've gone ahead and added that code and the results to this memory model picture. Over here on the left, I have the variable names. Now these variable names are only going to live in my code, and the compiler needs to know what variable names match up with which memory addresses. So it's going to store those in its symbol table. When it's done compiling, it no longer needs the symbol table, and this machine code over here will not require those, and so those will be removed unless we turn on debugging symbols, and then it'll store that for us. Talked about how to do that in a future lecture. Next up, so I've got the variable x here. It's stored at this memory location. Now, the compiler is going to reserve memory from high memory addresses to low memory addresses. So I started filling this in at the bottom. It's going to reserve all the space for all the local variables for a particular function at once. When I call a function, it'll reserve this next block of variables. So what we've seen is that x is stored at, and again, I've chosen different numbers than the demonstration I just did because those are not guaranteed to come out the same every time I run my code. So I've just I picked some arbitrary numbers. Indeed, an integer is 4 bytes, so the next variable, the y, is going to be stored 4 bytes after that. Y is 4 bytes, so the pointer will be 4 bytes after that. And here I've got the values. So 3 is stored in x at that memory location. 5 is stored in y at that memory location. And the pointer p actually stores a memory address. In this case, F130, which is the value, the memory address of x. So we can say that this pointer points to x. All right, just to demonstrate a little bit more clearly how pointers are working, I'm going to do 2 little experiments. First, I'm going to modify x by just x plus equals 4, so that should change it from 3 to 7. Then we'll modify x using the dereference pointer, and we'll go look at what happens when we print out all of these memory addresses. So I'm going to add another 2 to that same memory location using the dereferencing operator for p right here. All right, so let me go ahead, compile. I'm looking at this. This doesn't seem to be the same memory address. I'd have to flip back into my recordings and check for sure, but I think this did change. All right, so this is the very first block we had before. We can see we still have x is 3. It's stored at a location. 4 bytes after that, we have y. 4 bytes after that, we have the pointer, and the pointer still points to the same address as x. So this is all looking good. When we modify x, really the only change we'll see is right here, where x has now become 7, and the dereference pointer right there also changed. So both of those are a way to get access to that same memory location. And again, all these addresses are the same. Then we can modify x using the pointer. So this was that star p plus equals 2. And I see again it's changed both x and the dereference pointer. That's the same memory location. All right, back over here to the memory model picture. I can see that I've got, this is the original state of things. When I added 4 to the x variable, that's going to change that 3 to a 7, just like that. I love being able to edit PowerPoint and have the display up and record all at the same time. This is amazing. But that also changed where p, no, it didn't change p at all. P is still pointing to the same memory address, but the value in that changed. So I've got 2 different ways to get to that number 7 there. When I changed the pointer, the dereference pointer, I added 2 more to it. That 7 became a 9. And again, we accessed that same memory location using 2 different techniques. All right, I've added one more piece to this, well, 2 sections. So here, this was the last thing we did. We modified x through p. The new sections are right here. So all I'm doing in this piece is reassigning the pointer to point to a new variable. If it's not constant, I can have it point to pretty much any integer I want. I can move it around, which is extremely useful. To do that, I'm just going to look at line 36 right here. P is equal to the address of y. It reassigns the pointer. So we'll go verify that it's changed and now points at y in a moment. And then I'm going to modify that data, so not x. This used to point to x, now it's pointing to y. I'm going to go ahead and change that to 6 in this case, and we'll print out that same stuff again. All right, running the program. All right, so this is all before. We declared the variables, we modified x, we modified p. Here we are right here in this section. So we're going to reassign p to point to y. This is just p is equal to the address of y. And now I can see that p, this is the value stored in p right here, is exactly equal to the address of y. The dereference version should now match the value at y, and this is its current address, which is the same location. It hasn't changed. So p is still stored in the same memory location. Then when we modified p using the star p is equal to 6, I can see I've changed y to now equal 6, and the dereference pointer also equals 6. All right, so as I was going through this, the first thing I did was I went and I changed p so that it points at y. So this is what it looked like originally. I've got the address stored in p as the F130. That's the address of x. I'm just going to make a quick change. I'm going to delete that 0. I'll try that again. I'm going to delete the 0, and I'm going to upgrade that so it now points to 4. That's going to change my arrow a little bit, so we'll shrink that down, just like that. And now, the second thing I did was I went ahead and changed the value that in address F134 by just reassigning it to the number 6 using the dereference pointer. That's also, as we saw, changes y. All right, just a quick review of references, and I want to introduce how they fit into that memory model picture I've been drawing. So I've added this section here about references beginning at line 49. This is the key line right here. I'm creating a reference to an integer x. And again, if I wanted, I can put the ampersand over here next to the int to remind myself that this is a reference. We overload that ampersand. We use it lots of different ways. We're using it as the address of operator up here. In this case, if it follows a type, I'm creating an alias or creating a reference. So in this case, leave it like that for right now. I'm assigning that to x, and then I'm just going to print out x. I'm going to print out the address of x. I'm going to print out my reference and the address of the reference. Let me go ahead and just run this real quick. I compiled a moment ago, tested it out. So here's all that stuff I was printing before. The new stuff is down at the bottom under references. So I want to highlight right here that x is equal to 9. That's where we left off. Address of x is at B0 this time. And reference R is the same thing. And in fact, it has the exact same address. So when I add it to the memory model picture over here, right here, I have x and R. Both of those variables are the same thing. So the symbol table is just going to track them like this. Now the compiler has more or less two choices as it's going through. It can just keep track of R directly as a memory address, and that's what it's generally going to do for primitives, or it could use a pointer mechanism and just let us use it exactly as though it were a pointer without having to deal with remembering to put the star in and the address of operator. So it takes out the complexity. And inside the machine, it really could do either version, but that really doesn't matter for any of the work that we're going to be doing with references. All right, in a little bit, at the end of the lecture, I'm going to talk about parameter passing methods, and call by reference is a very common technique, and that's the main place where I use references in my code. So I'll introduce that for you guys. All right, to wrap this up, my notes say, don't forget to mention that references must be initialized when they're created, and they can't be changed, so they're constant. It also means that we won't ever be able to create arrays of references, so just a heads up there. All right, next up, I do want to go in and review arrays and put those into my memory model, so let me go ahead and put together some code to demonstrate that. All right, next, I just want to take a minute and talk about how primitive arrays fit into the memory model that we've been looking at. So here, the important stuff that I've added, I'm declaring a primitive array of integers with just 0 through 4, so it's got 5 elements. Those will each be 4 bytes, so it should take up about 20 bytes in memory, and I'll go draw that in the picture in a second. I'm also declaring a pointer that points to that very same array. And part of the reason I want to do this is I want to emphasize that arrays are just pointers, constant pointers, but there's a little catch there, and that's that the compiler already knows their pointers and they're constant, so it's going to just treat these a little differently. This doesn't get its own memory address that points to the 0. It just has the address of that first element of the array, and I'll show you that in a second. All right, I've got all of this stuff here, those first 4 lines, or so that I know how to draw this in the memory model. New stuff is right here. So here I'm printing out some information about A, the value of A itself, the dereferenced value of A, and the address of A. All right, then I'm printing out just the first 2 elements of that array, their addresses. I want to know which way to line them up in my memory model. And then some information about that pointer. So in this case, the value stored in the pointer itself, the dereferenced value. Hopefully that matches what we've got in the dereferenced value of A. And then finally, the address of the pointer. All right, let me go ahead and run this. I've already compiled. All right, so the new stuff is down at the bottom. These lines right here are just to help me remember to go put everything in the right spot. So we've got x at value 800 at 804. We've got y. The pointer is at 808. All right, check this out. The next thing we declared was the array. That's going to be at 820, beginning at 820. Part of the reason for the big jump is that it's actually storing the pointer first. So this was the last, y is at 08. The pointer is at 08. The pointer is going to be 8 bytes in a 64-bit machine because all of the addresses are 64 bits. So 8 bytes after the pointer here is going to be 810. And then we have the array after that, beginning at 820. So I believe this is actually 16 bytes after this point, and part of that is probably to align the memory in a certain way for the array. All right, let me go ahead and put these in the memory model. Oh, I'm not done yet. Hold on, Mike. All right, check this out. The address stored in A, or the value stored in A, is actually a memory address, and it's the memory address of the very first element. So this is at 820. The value stored in A is 820. So technically, A is a pointer, and let me pull this up. The symbol table is going to remember that. So let me grab PowerPoint, flip back to here. In my symbol table, I've got A. This is going to be a pointer for the array, but it doesn't need to remember that because it's constant. So the symbol table will just store the memory address of that. And anytime I use the dereferencing, as in when I use these brackets, this brackets is essentially the same as star a plus 0, star a plus 0, and then it's going to go get, I'm sorry, this one, star a plus 0. I'll write that in the notes in just a second. It's going to go get 0, get the value stored at that address. All right, but because the compiler already knows that, it's going to take care of all of those details for us. When we use the pointer version, if I declare PA, it's going to point to the same memory location, 820, and when I do the dereferencing, I still get that same thing. But this pointer is going to be stored at a different memory location. All right, let me go put all of this stuff into my PowerPoint memory model slide, and then it'll make a lot more sense than staring at hexadecimal numbers. Trust me, give me a second. All right, I've gone ahead and added everything to this memory model picture. I went ahead and moved some things around, and I actually lined the addresses up just to make sure I didn't make any mistakes. So there was a lot of hex digits. They were all the same up until the 7800. So I've just got the last 4 digits here. But these exactly match what we just printed out. So again, we have all this stuff from the early demo. R and X are the same. Y is here. P is a pointer to Y. That's where we left off. And then all the new stuff. I've declared an array. Array A, it told us that the value of A was the 7820 address. The address of element A0 also 7820. So inside the machine, the compiler is just it's not gonna use a separate memory address to store A. It just is gonna do all the translating in the compiler, and then the machine code will go faster if it doesn't need to do that extra step of dereferencing a pointer. All right, again, the values 0, 1, 2, 3, 4, they're each 4 bytes. It took some special effort to align the array at address 0. That's for performance reasons, because the modern machine architectures have vectorized commands that work well if things are aligned. So it did waste some space. It's got some empty space in here. Again, the pointers are 8 bytes, so they actually take up all of this space. OXF104 takes up this space and this space. This pointer takes up 2 rows. It just needs that much space to store it. And the pointer here is actually pointed to F120. Oops, I forgot to update those. Apologize, hope that didn't confuse anyone. I didn't go back and change the addresses to match exactly until after I'd done all this work. Forgot to update those. So again, pointer PA, pointer to the array, points to the same address, 7820, as the first element of the array. But to use it using pointer notation, the compiler is going to have to go and actually do the translation to figure out and follow that arrow. All right, just one more quick thing here. Down at the bottom, I've added 2 lines. This array indexing, so here I'm grabbing element 1 of the array. Inside the machine, if you read the assembly code, what it's really doing is taking that value A, which is a pointer, it's going to increment it, add 1 to it like this, and then dereference that, so go get the value. So I'm printing that out right here. Now, like I said, this command, square brackets, mean go get the address and add 1 to it. So it's just going to add those 2 things together. NA is a memory address. It's stored in the symbol table, but the machine code just is going to have that hard-coded in as a memory address. So it's going to add those 2 things together and dereference, which means that this also works because we can do addition in any order we want. We can take 2 plus A or A plus 1. Those are going to be the same thing. We can actually write it like this. I know this is confusing. I've never actually seen anybody write array indexing like this. Don't do it. You'll confuse other programmers. But it does happen to work. And that's going to be translated to this. And in a second, I'll just go ahead and run this and show you that it actually gives you the second value of the array. All right, here we go. So check this out. A indexing 1 does this inside and gives us the value 1. And the array has 0, 1, 2, 3, 4, 5. I think I stopped at 4. But this also works. I can write 2 index of A. It's just going to add those values together. This is an address. This is an offset to that address to go to the next memory location down. And it's going to grab that too. So when we do something like this, what it's really doing on the inside, hold on, is saying, so array 2 is right here. It's taking this address, adding 2 to it. 2 integers is actually 8 bytes. It does that translation on the inside without us having to worry about how big things are. And is going to go grab this value right here. So it computes this address, gets that value. And it doesn't matter whether I'm adding 2 to the address right here or the address to 2. Those are the same. All right, I just want to talk a little bit about creating dynamically allocated primitive arrays. We can do this a couple different ways. I'm only going to introduce the C++ version of things. C would use malloc. Go take 354, I believe, for that. All right, I just wanted to introduce the idea of dynamically allocated arrays and talk about how they are connected to this memory model, because dynamically allocated arrays are going to appear on the heap, which is a different section of the memory. All right, so here on line 74, I'm creating one. Now, remember that if I use this style array declaration up here on 57 with the brackets, that's going to be constant. And so I need to be able to give it the values right now. I need to know exactly what size it is. This is a constant pointer. This new operator is actually going to do some internal library functions built into C++ to go to the memory manager and get some memory. So we're not actually going to be able to use this constant style bracket notation to create this. So it must be a pointer. So to create dynamically allocated arrays, we need pointers. The new command is going to tell that memory module to go grab some space. In this case, I'm going to grab enough space for 3 integers, and I'm going to store the numbers 5, 6, and 7. This initializer list is optional. I could just create the empty array. This is just one way to fill it up easily to give me some demonstration numbers. All right, after that, I'm going to just print out a bunch of information about the array. And I think it's the same kind of stuff I've been doing up here. I'm just going to run this code, and then we'll walk through where everything is, and then I'll put it in my memory model picture. All right, now finally, anytime I use the new operator, I need to free that memory. This is just good practice. This will happen automatically when I hit this return in main and the program ends. But leaving this out is not good. If I've got a pointer to an array, I need to tell it it's a pointer to an array. Otherwise, I can just give it the name of a pointer to a primitive or whatever type it is if it's not an array. All right, one sec while I run this code. All right, so I left everything in there so we can see how things fit into the memory model. So I still got X. All of these addresses are at the 7FFEE090 kind of range of numbers. Okay, that's going to be on the stack. I can see here where I've got the address of DA. Let's go with address of DA right here is also on the stack, 7FFEE090. And this actually happens to be 040. This is greater than everything else, so it's going to be down at the very bottom. So all of these addresses, 030, 050. Okay. All right, in a moment ago I was doing my testing of this, and C++ has decided to rearrange it and put this pointer at a different location than when I was practicing. Check that out. This is actually going to be between this pointer and the other array. All right, I'll get in the right spot when I put it in the model. Anyway, then I can see that the address that's actually stored is significantly different. This is going to be on the heap, a different location in memory. So I'll go ahead and draw that in the picture and show you guys. And then DA0, when I dereference it, remember, anytime I use pointers, I can use the brackets to go get the same value rather than using that star. It's got 5 because that's what I put in there. And again, that address of this variable is over on the heap. All right, let me go draw this into my memory model picture and show you what it looks like. All right, I've gone ahead and added this new array to my memory model. So my dynamically allocated array is a pointer that's stored on the stack so that I can reference the array. I know where it is. And the value stored in that is actually the value of a memory location over on the heap. I'm with this, like, I put a whole bunch of extra digits in to just kind of emphasize that this is not on the stack. It's somewhere else in memory. And over here in this address, blah, 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 110, I've got my 5, 6, 7. So it's going to start lined up on a nice even number like 0, something that ends in 0. And this is where the array is going to be located. I can access that just like any other array with those bracket notations. It's going to take care of all that work for me. Just want to point out one little thing. That's some meta information that the memory manager needs to delete the array, like basically how big it is, how many elements do I free up, are stored in the address usually right before the array. So when I go and call delete, it gets this memory address. It's going to go back one and then free up this memory. So if you ever have an out of bounds error where you're off by 1, So this would be element 0, this would be element -1 or -2, depending on what size machine it is. You may be overwriting how much memory is used for this array. And if you put in a really big number, it might free up lots of memory, including lots of other arrays that you've stored on the heap. So just be careful. Don't have any out-of-bounds errors when you're using arrays, because C++ will not stop you. All right, before I move into multidimensional arrays, I just need to mention that character arrays are special. All arrays of characters are terminated by this null character \0. This is because a lot of the string libraries, particularly going back to C, working with character arrays, depend on this terminating character in order to figure out how long the array is. So I've got some examples here. First, if we look at this top line, character C1, so C++ is going to automatically determine that I've got 1, 2, 3, 4, 5 characters in this string. And so it'll create a character array of 5 characters if I do it like this. I've not included that null terminal character. So this is going to lead to problems when I start doing manipulations with strings based on these character arrays, because it doesn't have that null terminal character. And I'll demonstrate that actually right here when we print it out. There's already going to be an issue. This is the correct way to do it. I need to actually include that null terminal character. So this C2 array is going to have 6 characters in it because it needs to include space for that. If I declare an array automatically with the string notation, it will automatically include that null terminal character. C3 will have a length of 6. No problem, it's already going to be taken care of. If I specifically state that this array has a length of 5, the compiler knows that this string has a length of 6. It's too big to fit in there and will actually give me an error. Now, let me go ahead and demo this real quick. So write that, G++, file name. So here we go. This is the error. Initializer string for an array of characters is too long. So this actually has 6 characters in it because it needs to include that null terminal. I've only reserved space for 5. All right, so let me go ahead and fix this. First, that line will never work. It doesn't fit. I can't print it out if I never declare that variable. Need a semicolon there. Write that. G++ file name. Here we go. Now it's compiled successfully. Now, I told you there's going to be a problem because I didn't put that null terminal character in there. I'm expecting to get CS368 right here when I print that out. Then the next line down should also say CS368. That's what I'm expecting. Let me show you what really happens. I think I just compiled this, but I don't remember. Yeah, I did. All right, we'll run this code. And here's what I really get. Here's the first CS368, but because I didn't have that null terminal character, remember there's 2 ways. It's our job to remember how long the arrays are. C++ does not take care of that for us. And there's a couple ways people do that. You can actually specifically state the length, keep it in a variable, and just keep track of it that way. You could hard code it, not the best plan. Or you can use a sentinel terminated or a marker terminated array where you put a special character at the end that you can detect. It doesn't work great with integers because all characters are valid, but or all integers are valid, but it works pretty well with strings because the null terminal is technically not a valid character, and we can detect that. Because this is missing, it goes on and just continues to print whatever happens to be in memory next, which is actually the next string down, CS368. I'll go ahead and change that in a second, and we can see that it actually chooses the next set of letters. And this is that third string, the one declared with the quotation marks. All right, give me 1 second. Let me go change that. All right, I just went ahead. I made a copy of this so I can leave it in the template for you guys. Then I've added just some $signs to replace these. I just made a copy of this line. And then when we print this out, we'll see what is going on. So here we go, printing it out. I can see I've got my CS368 without that terminating marker character, the \0. And then it prints out the rest of the string until it gets to that marker character \0, which is present in the second string, which I replaced with $signs. And then this is from the string with the quotation marks. All right, let me pull up the memory model and show you what it looks like. All right, so I've got a conceptual picture here to explain what's going on. Now, it doesn't exactly look like this where all the addresses are lined up. So if you took another class that explained how this really works, please don't give me a hard time. I'm just trying to explain why we get that error. semantic error, I guess. All right, so I've got my variable C1. This was the CS368 without the null terminal character. It's the memory addresses that don't line up exactly right in the real world, but this is just for demonstration purposes. They're 1 byte each, so I renumbered them. Then I have the variable C2, which was an array terminated by that \0. It just happens to be in memory right next to this. So the fact that when I printed out C1, it prints out until it gets to the null terminal character, this was just a fluke that I happened to declare another variable that had a null terminal character right after it. So essentially, I just got lucky. And then when I printed out C3, this again was CS368 with a null terminal character. So I hope this kind of explains what we saw there. If you ever get a weird error like that, my advice, of course, is to don't use primitive character arrays for strings in C++. There's a string library. Use that instead. The only place that you're going to be forced to use it that I can think of off the top of my head, there's probably more, but legacy code and command line arguments are going to be in primitive arrays of strings. All right, one other little cool thing I want to talk about for a second, since it seems to fit right here, is that string copy function I had at the very beginning of the class. Overly complicated, very, very short, condensed version. Just want to go over this and talk about it. Now that we understand pointers and how strings are null terminated, this is where it really fits in the course. All right, so what I've done here is I'm going to be just copying one string to another using pointers. So I've got character array C2 here. This is the valid one with a null terminal character. I'm going to go ahead and put this back real quick so that I can actually copy the CS368. All right, next thing, I'm going to create a new character array over on the heap, and I want this pointer to point to the beginning. I don't ever want to change that pointer. I want a special pointer that I'm going to increment as I copy. So I'm going to create a new pointer and just give it the address of that string. In fact, I was just doing some testing. That's overly complicated. This is exactly what I need. All right, then this string copy, so S stands for source, D for destination. I'm going to go through. The first thing that happens is this D equals S. So this is an assignment. I'm going to go grab whatever character is at S. I'm going to dereference it and put it into the dereferenced D. All right, then the post increment operator happens after everything else. And in C++ is not specific about whether D is incremented first or S is incremented first. In this example, it doesn't matter. It's going to increment one, then the other. So now those two pointers will point to the second character in the array. So S will be pointed right here, and D will be pointed at the next spot over in this character array on the heap. Then it'll do this assignment. It'll copy exactly one character over. So I'm dereferencing both of them to get the value. Then after that operation is complete, it's going to do it again. Now this whole while loop, it's an empty while loop. I've just got a semicolon here indicating that it's empty. And the assignment operator returns whatever the value is of the character. So first thing I do is I copy capital letter C. That's going to be some ASCII code. It's just a number, and it's not 0. That's the only thing I care about, because anything that's not 0 is going to evaluate to true in a while loop. If you're curious, you can go look up the man ASCII page and see the exact value for these characters. But as long as it's not 0, then I'm good. It'll keep copying. As soon as I get to this null terminal character, what we'll see is that the first thing that happens is it's going to copy the null terminal character. Then it's going to increment both of the pointers. Then it's going to take a look at that return value from the assignment, which is the null terminal character. That's going to evaluate, it's basically 0 in ASCII. It's going to evaluate to false, and that's going to end this string copy. So let me go ahead and recompile this. We'll run this code, and we'll see that it actually prints out the right thing. Here we go. So now it's changed the value of C5, that's that new character array on the heap that I created, and stored the value CS368 in that. Let's go back and take a look at the code. Again, I was using pointers S and D because those are going to be incremented as I move along. And then C5 is the one that actually points to the data I care about. It's totally possible to reassign this. It's not a constant pointer, but I don't want to do that because when I'm all done with it, I want to delete pointer to an array C5 because I created that on the heap. left that out. Good practice. Let me go ahead and just remind myself anytime I use new, I want to use delete. All right, I just have a few array declarations here that can be a little more complicated than you might normally run into. And I just want to sort of walk through how to read these. So when you run across these in someone else's code or in code that I'm giving you for an assignment, they make sense. All right, so first up, the very simple one. This is the one I've been using the whole time. This is just declaring an array of 10 integers. Array of 10 integers. The second one here, this is going to be an array of 10 pointers to integers. In fact, this might actually be better if I were to write it like this. So I'm going to read this inside out. Pointers first. It's an array of 10 things, and those 10 things are pointers to integers. This array of pointers is really common notation when we have larger objects that I just want to keep a pointer to, so I can leave those objects on the heap. I don't ever want to make copies of them. I can save memory. So this is array of 10 pointers to integers. Okay, this next one will completely fail. Every time I'm creating a reference, and again, this I might think about trying this more like this, reading inside out. I'm trying to create an array of 10 references. This will not work. References must be assigned or determined at the time they're created. So this will completely fail. Compiler error. Okay. All right, this next one, again, I'm going to read it inside out. So this much first, inside the parentheses. This star is telling me that it is a pointer. Okay, so this is a pointer to an array of integers. So every time I'm declaring an array, I need to give it an address. What I'm going to give it is the address of an array of 10 integers. So let me go ahead and type this and be right back. All right, there's my comment. I could have also written this as just create a pointer, given an array. Both the array is already a pointer. This will create a pointer. This is doing the same thing. It's giving me a little more information as a programmer. I can tell it that I've actually got 10 things in my array. So that might be useful as a way to communicate with other people or even yourself in the future reading your code. All right, this next one is creating a reference. So read the inside first. So this much. It's creating a reference to an array of 10 integers. So this complicated notation is essentially doing the same thing as this one up here, except we're going to be able to get around using the pointer notation. References are going to be constant. I can't change it. It's just giving me a way to come up with an alias, a second name to use for array. So right here, this and this ARR and this ARR ref are going to be used exactly the same way. So a way to just create an alias, rename something. And finally, the most complicated one. All right, what I've got here, again, reading inside out. I'm creating a reference. I've got the little ampersand right there. This reference is to an array. So I see I've got my brackets there. An array of pointers to integers. So again, I'm creating a reference to an array of 10 integers, pointers to integers. All right, let me put that in a comment. I think I blurred the speaking too much. All right, there we go. Array is a reference to an array of 10 pointers to integers. Probably could have chosen a better name than just array at that point. Go ahead and just comment and add array alias. We'll name it that. Just to be a little more clear for you guys. All right, it's been about 3 hours since I recorded that last clip. I'm pretty sure I'm up to multi-dimensional arrays and then I didn't start this yet. Had meetings, then office hours, and then more office hours. Anyway, I'm back. Okay, so multi-dimensional arrays are going to be declared in C++ with just a second subscript. So in this case, I've got 3 rows. So the first one will be how many rows in the array, and 4 columns. And there's no limit to how many of these I can have. At least I don't think there is. If there is, it's big. I can also do multi-dimensional array 2, 3, 4, and actually give this initializer list. So this is going to be essentially a list of lists. Whoops, I'm thinking Python already. So I need an initializer list with 3 rows, and I need some commas here. And then I'm just going to put some values in here. So this is a row 1, column 1, row 1, column 2, row 1, column 3, row 1, column 4, and then row 2, column 1, 2, 2, 2, 3, 2, 4, and 3, 1, 3, 2, 3, 3, 3, 4. So this totally works also. I'll show that this compiles in just a second. Now in the memory, and I'll go ahead and draw a memory model picture in just a second also, there's no need to put in all of these extra curly braces. This, because of the way C++ is going to store this, it's going to put just all the memory as a continuous linear block. It's going to put 1, 1 in the first spot, 1, 2, 1, 3, 1, 4, then 1, 2, 1, 2, 2. They're just all going to be straight in a row. So I can create 3, 4 equals, and then just put all these things in just one list. So 1, 1, 1, 2, 1, 3, 1, 4, 2, 1, 2, 2. Hopefully I did something cool with the editing to make that smooth. We'll find out later. Anyway, this is the equivalent, but it's not quite as useful, not quite as descriptive for another programmer or for you in the future as to what you're really creating right here. All right, let me compile this, make sure it's actually running and I didn't make any typos. Oh, right. I actually made a note here. This line will completely fail. I was going to compile this and show you guys. An array of references. We cannot have an array of references. So let me go ahead, completely fail, comment this out. Try again, right. Compile. Time out, what did I do wrong here? Oh, that's dumb, I spotted it. I've got a semicolon right there in front of the equals. You guys have no idea, I just spent like 6 minutes staring at this. All right, easy to fix also. Delete that. There we go, no mistakes. All right, in a little bit, I'm going to be writing some functions that print out those arrays I just made, so I will be printing them, demoing that they work, they've got the right values. But for right now, I'm going to jump over and talk about that memory model. One sec. All right, so I hope this is pretty straightforward. When I put in a two-dimensional array, I've got my 4 entries in the first row, and just right after that, straight in memory, 4 entries from the second row, 4 entries from the third row. They're just all unwound into a linear array of numbers. All right, MDA over here, 0, 0 is going to be that first element. 0, 1 will be the second element here at 1, 2. The next row begins right here at 1, 0. We'll talk about subscripting those and grabbing just a row in a moment. Again, row 2 starts right here. When I do it this way with just one subscript, this is going to be a pointer to the beginning of that row. So let me pull that up and show, just demo some examples of grabbing data and grabbing rows from a two-dimensional array. All right, just a few quick examples of grabbing data from a two-dimensional array. I've got all my code here and what it prints out. So it might be easier to read this in output mode. Just wanted to show you guys that they match. All right, so as we go through, when I run this, I've got that multidimensional array with 1, 1, 1, 2, 1, 3, 1, 4 as the first row. I can just use the double brackets to index into a multidimensional array, just like a lot of other programming languages. So entry 1, 1 would be the second row down, second entry over, which was 2, 2. This next thing, not an exhaustive list of all the ways we can interact with two-dimensional matrices, two-dimensional arrays. Just wanted to point out some things that C++ is going to treat this as an array of arrays. So that second version where I was using all the brackets is really probably the most clear. But if I add stars to this, I can dereference an array. So this will give me a pointer to the first row. Remember, all arrays are just pointers to the first element. So I can dereference that to get the first element. And because it's an array of an array, to actually get to the element 0, 0, which is, well, I put 1, 1 in that spot. So when I print it out, it's going to look good in a few minutes. Yeah, that's this will just get me to the first one. Just wanted to point out the use of the double star right here. I can also use a lot of those other array indexing techniques. So in this case, I'm grabbing a pointer to the very first row. And again, this will be a pointer. and then I'm going to index at position 3, and that gives me the 4th entry over, because 0, 1, 2, 3 is the 4th entry, or 1, 4. And even more complicated, I got a lot of parentheses here because of the really low precedence of the star operator. But if we read this from inside out, MDA3 is a pointer to a pointer of integers. When I add 1 to that, it knows that there are exactly 4 items in the first row, so that plus 1 is going to jump down to the second row. It's going to move from, so it knows there are 4 integers in this first row, so it's going to jump down and point to the beginning of the first row, beginning of this row right here, row at index 1. All right, that's this highlighted part right here. Then we'll dereference that, and then take the, so this part does the math to compute the address. This part says, okay, trace that. So we're going to the pointer to that first element, and then we're going to grab the second index. So 0, 1, 2 is going to be the value 3. All right, I don't think I did the greatest job explaining that. I apologize. Listen to it twice if you need to. All right, let me talk a little bit more about making pointers to individual rows. One sec while I made some code. All right, in this example, what I'm looking at is just grabbing a variable and assigning it to one of the rows of my multidimensional array. The code is right here. Code is right here. What I'm doing, if I read this from inside out, I'm creating an alias or a reference with the ampersand. That alias is going to be to an array with 4 elements of integers. And the array that I'm looking at is actually from MDA 2. That's this data structure up here. And I'm grabbing row 1. So this is row 0. This will be row 1. So that's going to point to these 4 numbers right here. And then in my next piece here, I'm just going to go ahead and right here, extract out row 1. So row is a pointer to these 4 pieces of data. I'm going to index in and grab item 1. So this would be 0. That's 1. Should print out 2, 2 if I didn't make any mistakes. Let's give that a go. Yep, here we go. And I just copied that code so you can see again what I'm grabbing. Reading from inside out, create a reference. I'm naming it row. It's a reference to an array of integers, which is exactly what we had when we declared MDA2. And then just grabbing item 1, so 0, 1 is that number 2, 2. All right, give you one example of how to do that. Hope that was clear. That's why I spent a little bit of time doing all these complicated examples with how to read these from inside out. So you guys can actually create variables that bind a particular row. All right, just want to talk a little bit about looping over multidimensional arrays. If you guys have made it this far, if you've already taken Java, I'm sure you're familiar with using a double loop to go over an array with, for I equals 0 to length of the row, for j equals 0 to length of that row, and then index, matrix ij to do stuff with. I'm not covering that right here. I do want to focus on one of the new features available since C++ 11. That's going to be the range-based for loop. So for something, using the colon to say in this data structure, auto is going to be a new type that's just going to automatically determine the type from whatever I've given it here. So MDA needs to be something that's got elements in it. This is going to be the type of those elements, whatever it is. In this case, it happens to be an array of integers. So row here is going to be the first row of those integers. So it's going to be this row the first time through the loop, then this row the second time through the loop. All right, the next thing I'm going to do, because I've got an array here, this type is going to be an array of integers. Whoops, I missed. Row is going to be an array of integers. I can do the same thing and iterate over that row of integers. So in this case, each of these will be a reference to an integer in row. And then I'm just going to print out the entry in the matrix space. After I finish that row, I'm going to print out an end line. And this will print out the matrix. All right, I want to highlight too here that I need to create references to those rows so that it knows that actually the data type is right here. Here's the type of what we're looking at. Oops, I missed that much. So reference to an array of 4 integers. That's what I really mean when I said auto. I'm not sure I got all the words in there every time, but that's the type right there. Yes, and then this is just going to print it out. They need to be references so that C++ knows how many elements are in there. This is new to C++ 11. It's going to be able to go back and know that this has this size. What it means is that it won't work when we start passing arrays to functions, because that size information is not passed when we create the types of the parameters. They're just translated into pointers, and I'll demo that when the last part of this when I get to parameter passing, which is coming up next. All right, let me just real quick go ahead and write this, compile it, and clear the screen and run it. And just demonstrate that it is printing out the matrix. So this does work with C++. You do need the C++ 11 standard installed. So if you're working on a Mac using some sort of other IDE, you may need to engage that compiler flag for C++ 11. There's a post on Piazza with exact instructions how to do that. And I think there's a comment on Canvas, like the important information at the top of our homepage. If not, I'll go double check and make sure there's instructions right there. All right, next up, I just want to go over all the little details with passing parameters to functions. By default, if I don't do anything special, parameters are going to be passed by value. That means I'm going to be making copies. There we go. So here I'm creating a variable x, storing the value 3 in it. I'm calling my function, I named it don't change x. Because I'm calling by value, it's going to be making a copy. Down here is the function definition. I see that I've got a parameter x. Even though I'm using the same name, this is going to be a different variable. So it's going to get a brand new stack frame. It's going to get brand new memory allocated for all the local variables. First thing that happens is it's going to copy the value of whatever is in this x, 3, into the other x. So two variables with the same name, just like a lot of other programming languages, including Java. I'm changing that. This is going to change the local variable x to be 5. It's void. I'm not excuse me, not returning anything. And then I'm just going to be printing out x. When this function ends, the local variables are all removed from the stack. Technically, it doesn't take anything to the memory, it just moves the stack pointer. So that memory is still filled with whatever garbage was left behind by the function. But when it prints out x here, it's going to be printing out this x, which was 3. It was never changed. So let me run this, and then I'll pull up a picture of the memory model to like have a PowerPoint to point to. Okay, so I already compiled it. We run this code, and we see that x equals, oh, timeout. I forgot to actually print x. I just printed the x equals part, so I just added that in. All right, we'll go ahead and run this. Now we're getting x is equal to 3. It was never changed to 5. Okay, all right, so here's what's going on. In the bottom red circle here, I've got a stack frame for main. Somewhere in there, I've got a variable x, and it's storing the value 3. When I call that function, the don't change x function, it's going to store some meta information that the C++ is going to need to remove this from the stack after I'm done with the function. Essentially, the location of the base pointer that points to the bottom of the next frame. And then we're going to create a second local variable x. As the function executes, it's going to copy this value 3 into that x and then change it to 5 when it runs the code. As soon as it's done with that, it's going to pop this frame off, remove all of this information, and x is still 3 in our main function. All right, another feature of just basic parameter passing, as I pass in parameters, in this case I'm looking at my going, gone example, I'm calling a function called printStrings that's going to be given the string s. So I initialize s to going, then I'm going to print s, and then here I'm going to print s equals gone. Now, C++ is going to go ahead and evaluate all of these parameters and pass them to variables in the function. So printStrings takes a string x, a string y, and a string z. Now, as of C++ 11, the order of operations for evaluating the parameters is not specified. And on the CSL machines, this is going to happen right to left. So the very first thing that's going to happen is it's going to evaluate this expression right here, reassign s to be the string gone, and then s is going to be gone and s will be gone. So it's actually going to print gone, gone, gone. Let me just demo this real quick. I just tested it, I ran it. Let me bring up the shell again. Here it is. I can see up at the top, gone, gone, gone. One more little quick experiment I can do. Let me go ahead and add one more detail. Let's make this the middle string. This probably would have been a better demo, but then you lose the going, going, gone expression. Anyway, so what I've done here is I've just switched the order. I'm going to print S first. This is going to be evaluated first. It's going to be the word going. Then this is evaluated next. It's going to change S to gone and send gone to the function. So that'll be mapped to Y. And then S has now been changed to gone. It'll be over here. And gone will be sent here. So we'll have gone, gone, going when we run this. All right. Let me go back to the shell. And right here is that gone, gone, going. So just a heads up, depending on the system, in the version of C++ you're using, you may run into issues where the order of operations of things being evaluated in parameter lists are backwards from what you'd expect. So heads up and be aware that that can happen, and you can prepare for that. All right, next up I wanted to introduce the idea of call by reference. I'm just going to quick make a copy of the don't change x function. Instead of calling don't change x, we're going to be calling function call by reference. All right, I'm going to make a copy down here of this function, bring it up so they're next to each other. It's been renamed call by reference. And the only thing I'm going to do differently is I'm going to add an ampersand right here. Let's see, is it in insert mode? There we go. I need to go ahead and add the prototype to the top so this works. So let me add this right here. And that needs to be replaced with a semicolon. Okay, so again, I'm now, when I call a function, essentially all of these lines are like, here's the variable declaration, int y equals, and then whatever's in the parameter. String x equals whatever's in that parameter list. Int reference to x equals whatever's in that parameter list. And remember, the reference version is just creating another name for that same variable. So this will actually let me use the value, the data in that variable right here, x, when I do it. And so this function, call by reference, will in fact change x to 5. And when I print it out here, if I haven't made any typos, we'll see that it's changed. All right, so let me write this. We will compile, and we will run this. And we can see that initially x was 3. That never changed. When we ran it again after the call by reference, x changed to 5. Okay, there's a couple of very good reasons to use call by reference. It's essentially on the inside just creating another name that points to the same data, and that can either be done with pointers, which I think is what's going on when we use passing things to functions. If it's all in the same function, it's just going to the symbol table in the compiler will take care of that without any overhead whatsoever. But it avoids the overhead of copying and lets us do, I guess, what's known as centralized updates, where I'm changing one variable based on another one, updating a piece of data using a reference to it. Okay, yet another version of this. I'm going to, again, just do some live coding. I'm going to make a copy of this one. Instead of call by reference, I'm going to call by pointer. Okay, and we'll change, we'll give it, here's what I want to do. Yeah, let me grab these 3 lines, paste those again, and change the name. Call by pointer. Now instead of giving a reference to x, x is now going to be a pointer. And I'm going to need to dereference that right here. So now when I call like this, a pointer, if I'm declaring a pointer, int star x equals, I need to give it the address of something. Address of what? Whatever, something like that. Something else that's an integer. So when I call this function, I need to do the same thing, because this is going to be create a pointer, I need an address. So in this case, I need to put the address of symbol right there in order to make this work. I'm going to change x to, replace that with a 7 this time. There we go. So we'll dereference, x is now going to be equal to 7. Put my space back. That looks good. And now, let's see here. Let me go back up to the top. Paste in this. Void and that looks good. Not quite. I pasted the wrong line. What am I doing? Int star p. All right. Again, in function prototypes, the name doesn't matter. I just typed p because I was thinking pointer, but this will completely run. In fact, when C++ goes through and looks at all the prototypes, it doesn't remember the names. All it needs is that this is a pointer to an integer. They're almost always there. There's no disadvantage to including them. It's useful for other programmers and me next year when I come back and give this lecture again to know that I had a pointer. All right, next up, let me just go ahead and save this. We will compile it and run it. One sec, I'll just go ahead and do that off camera. Okay, I went ahead and compiled it, I ran it, and the result is that x is now in fact indeed changed to 7. I didn't print it out inside the function. I did that way down here after the function was called. So just one more version where I can call something and change it. Now, where might I choose these things? This is the way that I would almost always do things, call by reference. If I want to just avoid the overhead of copying data, if I'm not going to change it, this is my preferred version. And in fact, if I know I'm not intending to change it, I'll add the keyword const right here. I'm changing in this function right here, so this would be a bad choice, a bad example. But this is my go-to if I'm just needing to avoid the overhead of copying data. If I want to be clear, if I'm writing a function that someone else will be using, I'm going to come back and I'm going to use my call by pointer version because they're going to have access to the all of the prototypes, and they'll know that this function is taking a pointer. They may not have the actual definition if I'm working for a software company and providing an API for someone else to use, but they'll have access to how do I call all of the functions. And when they see that this is called by pointer, then they know that they will need to give it the address of a variable. And there's a strong chance that this variable will be changed. So this is a clue to your user that there may be a side effect. I may be changing x, and if I don't want x to change, I need to make my own copy and give it to you. Just a quick note on functions that return pointers. This is very common to return a pointer, but we have to be very careful with this. Right here, I'm creating a string h, and it's just the ha with a space after it. I'm going to create a new string. This is a pointer to a string maniacal. I'm going to call my function duplicate x times. I'm going to give it that string and how many times I'd like to duplicate this string. And then I'm just going to print it out. So I'm dereferencing here. Here I'm creating the pointer. Excuse me. So my function is going to be returning a pointer. So the return value goes in front of the name. I've got a return value right here. Function name, I'm giving it this string. And again, I don't want to deal with the overhead of making a copy of a string when I can just use that directly. I have no intention of changing my string h over here. So I'm going to make it a constant. Here we go, const and reference. So I can just use that data directly without worrying about my function changing it on the inside. If I'm giving this prototype to someone else to use my code, they can see the prototype and very easily know that this function will not change their data because it's const. I'm also going to give it the number of times to duplicate that string. And here's what we're doing on the inside. I'm creating a new result string. I'm going to assign it initially to the value h, create a little loop that's going to go through x times, and just say s is equal to s plus s. And then I'm going to return the address of that pointer because it returns a pointer. So whatever the return value, the variable that I store it in needs to be a pointer. So I need to give it the value s. All right, this looks like it should be good, but there's a problem. And in fact, the compiler is going to give me a warning right away. Let me pull that up. All right, here it is, right up here, warning, right there. The address of local variable s is returned. So what I've done is I've created a local variable in the stack frame for that function. The moment that function returns, that variable is no longer available. There might be some useful stuff still in there, but the moment I call another function or create another variable, it's going to be overwritten. So it might work, it might not work. This is very bad practice. All right, in fact, when I tried to run this, it gave me the error message, command terminated. Here, it printed out all that stuff. It got to the line where I was printing out the string and failed. All right, so to fix this, I've got a couple of different solutions I can use, and none of them are great. But the best one is to, instead of just making string s a local variable and copying it, instead what we're going to do is create a new pointer to a new string on the stack. So I've kept all of this code as it was, but here, before I return this, what I'm going to do is create a pointer to a string, create a new string, so this string will be available on the heap. It's not going to be lost when the stack, when the function ends and that stack frame is deleted. I'm going to initialize it with the string that I just created here, my local string. So this is making a new copy of that. This is extra work. There's probably a better way to do this, but I thought this one made sense from like an instructional point of view. I need to create a string on the stack, and I didn't want to mess with my code too much. And that's what I'm going to be returning. So before I had %s here because I was returning the address of this local string. Here I'm just straight up returning the pointer. So let me just show that this works. So go back to the shell where I compiled it and then ran the code. I'm printing out ha 32 times. So we're laughing maniacally. Ha 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 ha. All right, I had fun with that. But the downside to this is I'm using the new operator here inside of a function. It's going to be up to the caller to go back when they are all done with this and delete the string. In this case, I called it maniacal. When we're all done with it. And they need to be warned. So if I'm writing an API for another user or something, I need to put in the comments that they need to call this function delete when they're done exactly once. And that can be tricky to do. Memory management is one of the most difficult things that C++ programmers run into. It's the root of almost all the really bad errors out there. All right, so some other solutions would be to use a global variable or to use a static local variable that we can then return. And those both have their own problems too. If some other function changes the global variable while I'm not paying attention, or if I call the function again with a static local variable, it'll change both my maniacal plus wherever else I've called that function. If I gave it another variable, they all get changed because there's only one copy. I'm not going to go into more details about static local variables. That's kind of getting away from my talking about parameter passing. One last thing. All right, so we just talked about returning by pointer. Now I want to talk about returning something by reference. So here's my example right here, beginning with this string. It's a quote from Johannes Strostrup, the inventor of C++. If you think it's simple, then you have misunderstood the problem. One of my favorites. So here's what we're going to be doing. We're going to find the alphabetically last letter of that quote. All right, and just put it into a character C. Now, the primary reason I would ever want to return something by reference is to avoid the overhead of copying. Here, I'm actually making a copy because I've just got char C is equal to, this is going to return a reference to something. So in order to avoid that overhead of copying, what I would really like to do is put in, there we go, it finally let me do it, put in an ampersand right there. This has been a real problem all afternoon. This morning it was working great. Now my connection to the CSL machines is so poor. It's missing characters I'm typing. It's driving me crazy. All right, we want to return a reference and store it like that. They will both work without the ampersand. It's going to make a copy. Now here's the idea. I've got a find alphabetically last letter wrong version right here. This is not going to work. It'll give us an error. But the idea here, it kind of makes a lot of sense to people, and it's a really common mistake. So I want to just show you the wrong version and then how to fix it. So here's the idea. I'm giving it a string that I have no intention of changing, constant reference to a string. I'm going to assign the max char equal to the very first one in the string, so it'll be that I right there. Then I'm just going to go through, use my range for loop, and just iterate through the data, so all of the characters in the string. So the first time through it'll be an I, the second time through C will be an F. If that character is bigger than the maximum one I found so far, and I just made a copy here of the first character, then I'm going to upgrade that. So the max char will now be a copy of whatever the biggest one it finds it. The alphabetically last character in this string is actually the Y right there in U. That's the one it's going to find. So this is going to return that max character. Now, what it's doing is actually returning a local variable. This is a reference to a local variable on the stack, which will be deleted as soon as this function ends. It might be deleted, maybe not. It might still be there, but eventually the program will overwrite it. All right, so this is, in fact, to give us a warning when we compile this. Let me go ahead and bring that up and show you what it says. There we go. Warning, reference to local variable max char return. So that's not a good plan. Now let me go back, scroll down a little bit where I've got a better version here. So find alphabetically last letter. I took out the const right here in case you wanted to change it. This is how you do it. If you want it to be a const and never change the string, that's not a bad idea. Throw in const right there. You'll have to also return a constant reference to the character. Otherwise, we're going to be, the error message is discard the qualifiers. Const is the qualifier. So if you ever see that error message, so we'll need a const right here. And then we'll also need to be able to, so this will, one moment, let me just walk through how this works. So what I'm doing is I'm going to look at the index. I'm going to be returning something that has a lifetime that exceeds the duration of this function. So basically, I'm going to be returning a reference to one of my parameters. That's almost always what I return, as a reference to a parameter. It's going to avoid the overhead of copying. I've got huge parameters. These are big. Could be a gigantic string. I don't want to copy it. Could be like a collection of different DNA strands from animals, genome sequences. Something big is where I would use this, and I want to be efficient. So I'm going to send in a constant reference, and then I'm going to get a constant reference back so I don't have to copy something back out of the function. So, but the strategy here is I'm going to be looking for the index of something in this. Obviously, a character in a string is only 1 byte, not a big deal as far as size goes, but I just wanted something that illustrates the strategy. So I'm going to go through all of the different indices using a different style loop here, check it out to see if that value is bigger, and I'm going to track the maximum index. And then what I really want to return at the end is a reference to one of the pieces of data in my string s. So in this case, it's just a part, just one of the characters, the one at the max index of the string. And that's going to be returned as a constant char reference. So I made a couple changes as I was going through this code. Let me go ahead and add this up here, find alphabetically last. I changed this to const so that it's I can use a const string. This is probably the most likely scenario you'll encounter this. If you do want to be able to change your string using the, find the maximum character and then go back and change it, leave out those consts. All right, and then next up, when I called the function, I believe yes, right here, I just put this in a character. I'll need to make that const also so that it doesn't discard that qualifier. All right, let me write this. Let me compile and run it, and we can see that the alphabetically last letter is indeed Y, just like we expected. All right, again, a little bit with the const because that can be confusing. If I do something, so const and reference combined, I need the const if I'm returning a const reference, so I don't lose that. If I'm just making a copy of it, then I would leave out the reference. It no longer needs to be const. This is just going to find a copy of that, make a copy of the result. So this piece right here is going to be a constant reference. But when I assign it to the new variable, this is going into a completely new memory location that's not been designated as const. Let me show you that this works. All right, so I compiled it. I still have that old function there with the warnings. Ran it, and I can still see that this works. This is the one that I can change now. But it's not connected to that string. It's no longer a reference to a piece of the string once I just made a new variable and assigned it to C. All right, so next up, I need to talk a little bit about passing arrays and multidimensional arrays to functions, and we'll call this good from right there. All right, I just went back and wrote some more code. I hope this is working well, where I pause the video, write the code, and then come back and just talk about it. I know it probably makes it hard to keep up if you're trying to type all this at the same time and follow along. I apologize for that, but I think it's a lot smoother when I type first and then talk about it. So here's what I'm doing. I'm creating an integer array with numbers 1, 2, 3, 4, and then I'm just calling a function printing array. And to pass an array to a function, if it's just a simple array, I can just give it the name like this. Well, as a parameter, I just give it the name. Let's take a look at print array real quick. That's found right here. So print array, when I put the parameter in, remember I'm getting int array equals something, and what this is going to be equal to is this array variable. So I need to tell C++ that it's an array, and that's what these brackets do. Also, C++ is going to discard any of the size information as an array is passed into it. In a second, I'll write another equivalent version of this and show you what that looks like. Because C++ is going to discard the size of all primitive arrays, I also need to pass that if I need anything related to the size, like if I want to iterate through the entire array, or if I want to do any bounds checking to make sure that it's not going to break something. In this case, all I'm doing is iterating from I equals 0 to the size that I gave it, and it's just going to print that out. All right, I've got a couple functions here. I've got increment array also. Remember that arrays are pointers, and so when I pass by an array to a function, it's still passed by a value, but it's passing a pointer, just like when, so it's making a copy of that address, which means that I can use that copy of the address to go ahead and change the array. In this case, I'm just using a loop for I equals 0 to size, and I'm going to increment that. And then right here we print it out again to show that it's been incremented. All right, so let me demo that this works. Right, we will save it and run it. Give me a sec while I do that. Okay, got it compiled, ran it. So here's all the other stuff from earlier. Here's a copy of that array, 1, 2, 3, 4. I've incremented it, and I get 2, 3, 4, 5. So it does indeed change the values in the array. All right, there are two other equivalent ways to write this function prototype. So I'm going to go ahead and make copies of this. The first one is this one right here, int array with the brackets. I'll keep that. The second way is to remember that this is just a pointer. So I can insert the star here, get rid of those brackets. This is equivalent. This is going to work exactly the same way. I'm just creating a new parameter that points to that array in the main stack frame. All right, and the third way to do this is to go ahead and put in an actual number here to tell it how many parameters there are, tell it how many elements are in the array. This is completely ignored by C++. It doesn't care what you put there for a single dimension array. When we have a multi-dimensional array, I'm going to do that in a second. It does matter. We'll have to put in numbers for every element or every dimension except the first one. The first one doesn't matter. All right. Actually, let me go ahead and I'm just comment out these two guys, and we'll leave that first one. You have these for reference when you download the code at the end of lecture. All right, let me just wrap up by talking about passing multidimensional matrices, primitive matrices, to functions. So here I'm declaring a multidimensional array, or a matrix. Again, this is just copied from above. It's the same one I was using in my earlier demonstrations. And then I'm going to call a function print 3x4 matrix. And a lot of the same rules that I just went over for primitive arrays apply here for multidimensional. The exception is I'm absolutely required to put in the dimensions for all of the indices except the first one. So this is sort of the default version of what's going on. C++ needs to know how many pieces are in each of the rows, but it doesn't actually care how many rows there are in the matrix. So I'm required to put in everything but the first right here. This code just goes through, it's got the double loop. For I goes from 0 to 3, for j goes from 0 to 4 for a 3x4 matrix. I hard-coded that rather than passing sizes in. And then it's going to just print out the matrix. Let me go ahead and run this, and then I'm going to talk about two different versions of how to declare the matrix up here. All right, actually I just compiled, I did run it. Here it is, all the garbage from earlier in the lecture, and here's the matrix that it prints out. So it's working just fine. I'm going to make one little change right here. I'm just going to put a typo in the name of my function right here. So let me insert keyword completion. Why? No. All right, timeout. I gotta fix this. All right, so I've made a typo in the name of the function. Got that fixed. I just added a bunch of garbage to the name. And what I wanted to show you guys was the error message that pops up with this function has no prototype. So let me go ahead and run this. What it's telling me is there's an undefined reference to the function that I'm calling, because I just took that out. And what it's looking for is this as the type of the input. So what this is telling me is that I need the name of my variable, and I have the type here. So when I call print matrix, it's got to have this type, int. And it's telling me that the first, when I read inside out, the name goes right there between the star and the parenthesis. What this is telling me is that it's a pointer to, and again, arrays with 4 elements of integers. Read this from the inside out. But the error message will tell me exactly what I'm screwing up. So another way to write this would be to go back over here. Let me put the name back. There we go. Instead of a matrix like this, what I can also write is star matrix. I need to give the name right there. And then, again, so this is a pointer to an array of integers. And again, it doesn't care how many rows. So essentially, this is a row of the matrix. It doesn't care how many there are for the function. All right, so this is another way to do this. Let me compile this and just verify that it still works and that I didn't make any mistakes. All right, yep, looks like it's still working. Let me go ahead and run this. And see, yep, still printing the exact same thing. So this syntax also works right there where I'm using the pointer version. The other thing I can do is I can actually give it both dimensions. There's nothing wrong with putting in matrix 3, 4 and just letting C++ know that there's a 3 there. It's going to completely ignore that. It will not retain this information. It's just going to translate it into a pointer to arrays with 4 integers. All right, I'm going to wrap this up here. Let me go put the video through editing and then get it put up on YouTube. I'll send you all an email when it's ready. And until then, have a great day.